Good morning, students. Today's topic in physics is atmospheric pressure. So this is somewhat tricky topic. So concentrate yourself. This is very important topic as far as papers are concerned. So we are going to start. We have air molecules around us which take up space and have weight. They make frequent collisions with things. Forces acted. Atmospheric pressure exists because of the molecular bombardment of these energetic air molecules. At sea level, atmospheric pressure is about 10 raised to the 5 pascals, which is also called 1 atmosphere. We do not normally feel the large atmospheric pressure because of the pressure inside our bodies is almost the same as the external pressure, that is 1 atmosphere, and so balances it. At high altitudes where the air pressure is less, breathing is difficult and nose bleeding may occur. Hence, modern aircrafts have pressurized cabins in which air pressure is increased sufficiently to safeguard the passengers and crew. The atmospheric pressure is equal to the pressure exerted by a column of mercury 760 mmHg. The atmospheric pressure is also equal to the pressure exerted by a 10-meter length column of the water. Here is again very important topic, that is air popping. The middle part of the air is normally filled with air at the same pressure as the air outside the body. The air pressure can adjust because when you swallow, the eustachian tubes in your throat open and air freely enters or leaves the middle ear. For example, if the air pressure is greater outside the body and in the mouth, when you swallow, more air will enter the middle ear to raise the air pressure there. Here is a diagram of the full outer ear, middle ear, and the throat. This is eardrum, which actually moves because of the difference of the pressure. And here is eustachian tube to the throat. If you travel in a car which quickly climbs a steep hill, your ears sometimes pop. Pop is actually a sound that is like a whistle. When you feel a whistle in your ear when you quickly climbs a mountain. This is because you are rising rapidly into the atmosphere where the pressure is lower. The popping sensation is caused by the air pressure being lower in the throat and outside the body than in the middle ear. Because outer pressure is lower now and inner pressure is greater now, and this is the pressure difference that is actually causing the popping sound. The difference in the pressure causes the eardrum to push outwards. When you swallow, the air pressure in your middle ear reaches the same pressure as the air in your throat and outside, and the eardrum moves quickly back or pops into place. A question is here, what happens if the air pressure in the throat and outside the body is less than the pressure in your middle ear when you swallow? We will feel a popping sound in the ear. Another question is, if you ride quickly down a hill on a bicycle, your eardrums are pushed in before they pop back. Why is this? Again, because of the difference in the air pressure. Because the outside pressure will be greater now and inside the pressure will be lower now. That's why eardrums are pushed in. If astronauts are not in pressurized space capsules, for example, when on a spacewalk, they must rely on space suits for supplying a suitable atmosphere because space suit actually provide an equal pressure as outside of the spacesuit. Otherwise, a blood and water in the body would boil and possibly explode. This will be because of the pressure difference. Similarly, likewise, divers meet high pressures and different dangers. If they breathed air, extra nitrogen might dissolve in the blood, and on returning to the surface, they would suffer the painful and sometimes fatal condition called bends. This is caused by the dissolved nitrogen forming bubbles in the blood. To prevent this, they breathe a mixture of the oxygen and helium. This is why actually they carry cylinders that is actually a mixture of oxygen and helium through which they inhale. If divers have been working in deep waters, for example 500 meters, they are brought to the surface in a diving bell and kept in a decompression chamber for up to several days while the pressure is slowly reduced. Otherwise, if they suddenly take to the surface, they will feel bends because of the pressure difference. So this is why they normally kept in the decompression chamber for several days to maintain the pressure outside and inside to neutralize the pressure. The unit of the pressure used for meteorological purposes is called the bar. It is defined as a pressure of 10 raised to the power 5 pascals. Therefore, the atmospheric pressure at sea level is also given as 1 bar. 1 bar is equal to 1000 millibars. 1 bar is equal to 100 kilopascals. These are very important concepts. That is normal atmospheric pressure. The normal atmospheric pressure is given exactly as 1013 millibars. Very high atmospheric pressure goes up to over 1040 millibars and very low ones down to 950 millibars. On weather maps and charts, places where the atmospheric pressure is equal are joined by lines called isobars. Wind, which is the movement of the air, blows from areas of the high pressure to the areas of the low pressure across isobars. The closer the isobars, the stronger the wind will be. Here are isobars. In the northern hemisphere, the wind direction around a low pressure region is anti-clockwise and clockwise region and clockwise around a high pressure region. The converse is true. So here is the high pressure. The wind direction is clockwise and here is low pressure. The wind direction is anti-clockwise. The wind blows along the gaps between the isobars. Here are isobars. However, it blows perpendicularly inwards as it crosses an isobar. When the isobars are close to one another, indicating a great pressure gradient, strong winds are expected there. So, closer the isobars, strong wind is expected. Far are the isobars, light wind is expected. The large arrows shows the general direction of the massive wind movement blowing from a region of high pressure to a region of low pressure. So normally wind moves from high pressure area to low pressure area. A question is here, express standard atmospheric pressure in Newton per meter square. Assume the density of the mercury is 13.6 grams per centimeter cube and G is 9.81 meter per second square. Standard atmospheric pressure is 760 mmHg. Density of the mercury is given 13.6 gram per centimeter cube. First, we will convert the density of the mercury in kilogram per meter cube. So, this is the method to convert, because we have to divide this value with 1000 to convert grams into kilograms, and centimeter cube will be converted into meter cube by dividing 100 into 100 into 100. So this is the method. Acceleration due to gravity is also given. Standard atmospheric pressure in Newton per meter square is HdG. Height is given, that is 760 millimeter Hg. So this millimeter will also be converted to meters by dividing by 1000 and putting all these values into the formula. Answer will be 101 400 Newton per meter square. So do it carefully. And first part is done. Second requirement is converted it into bars. So from Newton per meter square to bar, the method is divide the value with 10 raised to the power 5. So divide this value with 10 raised to the power 5 will convert Newton per meter square into bars. Solving this value 101 400 divided by 10 raised to the power 5, solving it on the calculator will give us the answer 1.014 bars. And C's part requirement is millibars. So in 1 bar there are 1000 millibars. So multiply this value with 1000. Answer will be 1014 millibars. Next topic is barometer. Barometer is used to measure the atmospheric pressure. Here is a figure. Here is vacuum, here is mercury, and here is a tub that is containing mercury. Here is a glass tube, here is a scale. A mercury barometer can be made by filling a long glass tube about 1 meter long with a mercury and then turning it upside down in a bowl of mercury. The column of the mercury is held up by the air pressure. As the air pressure varies from day to day, depending on the weather, the height of the mercury varies. A height of 760 mmHg is called standard atmospheric pressure. The greater the atmospheric pressure, the greater the vertical height of the mercury column, and vice versa. A question is here. Calculate the atmospheric pressure in pascals when a mercury barometer sports a column of mercury 76 centimeter high. Density of the mercury is 13,600 kilogram per meter cube. Formula for the atmospheric pressure is HdG. Height is given, that is 76 centimeter. We will convert this centimeter into meters by dividing 100. So answer will be 0.76. Density is given 13,600 and G's value is 10. Solving it on the calculator will give us this answer, and unit will be Pascal. And other question is here. A barometer reads 75.5 centimeter of mercury at the foot of the mountain and 65.5 centimeter of mercury at the top of the mountain. Estimate the height of the mountain in meters. Assuming the density of the mercury is 13,600 kg per meter cube and the average density of the air is 1.25 kg per meter cube. So first we will find the pressure at the foot of the mountain. Formula will be HDG. And height is 75.5 centimeter. We will convert this centimeter into meters first by dividing 100. So the answer will be 0.755. This is the height of the mercury at the foot of the mountain. Density, that is given 13,600 and G's value is 10. Solving it on the calculator will give us this answer. Now we are going to find the pressure at the top of the mountain. Formula will be again same. But now height is 65.5 centimeter. Again, first convert this centimeter into meter by dividing this value by 100. Height will be now 0.655. Density is 13,600 and G's value is 10. Solving it on the calculator will give us this answer. And now pressure difference is 102,680 minus 89,080. So this is the pressure difference. Now we will use again the pressure formula, that is HDG. Now pressure difference is this. Height of the mountain is required. Density of the air is given 1.25. This is the density of the air. G's value is 10. Solving it will give us this answer. So this is the height of the mountain. And other question is here. The height of the mercury barometer is H. This is the height of the mercury. When the atmospheric pressure is 100,000 pascals. What is the pressure at the X? This is the requirement. So at this point, pressure at X will be H minus H by 5 because this is the total height, and at this point pressure is required. So H minus H by 5 of the atmospheric pressure, and atmospheric pressure is given 100,000. So we will put 100,000 over here. Solving it on the calculator will give us this answer. And other question is here. The figure below shows a simple mercury barometer that can be used to measure the pressure of the atmosphere. On figure, mark a vertical distance that would provide a measurement of the vertical pressure. So this is the vertical distance that shows the atmospheric pressure. Second requirement is state and explain what happens to the level of the mercury in the tube when atmospheric pressure is increases. When atmospheric pressure is increases, the height of the column will be rise. So the level of the mercury column in the tube increases because the mercury column inside the tube is supported by the force due to atmospheric pressure. When atmospheric pressure increases, the force is greater. Therefore, a higher mercury column can be supported. And other question is here, will the mercury column be higher or lower than 75.5 centimeter when the whole setup of the simple barometer is taken to a high mountain top? Explain your observation. At the top of the high mountain, there will be less pressure. So height of the column will be lower. Answer is here less, because the pressure of the surrounding air is less than that at a sea level. This is because at greater heights air is thin. Next topic is measurement of the gas pressure. Bourdon gauge. A Bourdon gauge measures gas pressure above that of the atmospheric pressure. When a gas supply is connected to it, the gas pressure causes the curved metal tube to uncoil a little. This movement is magnified by levers and moves a pointer over a scale. This is the pointer. Bourdon gauges are used as tire gauges at garages and also as gas cylinders gauges. Next topic is manometer. Manometer is used to measure gas pressure. It measures pressure difference. Here is the gas supply. This height difference is equal to excess pressure in millimeter of the mercury. And here is the mercury. A manometer consists of a U-tube containing a liquid, either water or mercury. The one in the diagram is filled with mercury. The height difference shows the extra pressure that the gas supply has in addition to the atmospheric pressure. This extra pressure is called excess pressure. To find the actual pressure of the gas supply, you add atmospheric pressure to this excess pressure. The actual gas pressure can be measured by using the equation, and this is the equation to find the actual gas pressure. Formula is P is equal to P naught plus HdG, where P naught is the atmospheric pressure, D is the density of the liquid, G is the gravitational field strength, and H is the difference in the height of the columns. A question is here now. An engineer uses the mercury manometer shown in the figure to test the pressure of a gas supply. Question is, write down at which of the points A, B or C the pressure is greatest. So C is the point where pressure will be the greatest and the pressure is smallest. So B is the point at which pressure will be the smallest. Another question is here. Figure shows a manometer containing mercury of the density D is equal to 13.6 multiplied by 10 raised to power 3 kilogram per meter cube connected to a gas supply. Here is the gas supply. Calculate the pressure of the gas supply in units centimeter, Hg and pascals. Take acceleration due to gravity is 10 meter per second square. Atmospheric pressure is 76 centimeter Hg. So given length column of AC, here is the AC, that is 5 centimeter. First we will convert into meters by dividing this value by 100. So answer will be 0.05 meters. Atmospheric pressure is 76 centimeter Hg. Now PB is equal to, so this is the PB, that is the gas pressure, P naught plus pressure due to mercury column AC. So 76 plus 5, this is the 5, this is 76 centimeter, both units are in centimeter. That will be equal to 81 centimeter Hg. So now the step is, because the requirement was centimeter Hg and the next requirement was pascals. So now we will convert this centimeter Hg into pascals. To convert centimeter Hg to pascal, formula is HdG. So height is now 81 centimeter. Divide this value with 100 to convert it into meters. Density is already given in the standard unit, that is kilogram per meter cube. And G's value is 10 meter per second square. Solve it on the calculator will give us this answer. Okay. Next is the demonstrating atmospheric pressure. When the air is removed from the can, there is nothing to resist the outside pressure and the can is crushed like this. Air removed by the vacuum pump, atmospheric pressure crushes the can. Now we will watch a video that will show how the pressure difference can crush a can. So, here is the video. First, water will be put in the can, then boil it on the flame. The boiling water will result the density of the air less denser. Air will move out of the can. There will be less pressure inside the can now. Here is the cold water. Here is the ice water. So now put it into the cold water. And look, the pressure difference will crush the can. Here is crushed can. The normal atmospheric pressure is 1 atmosphere. 1 atmosphere is equal to 1.013 multiplied by 10 raised to the power 5 pascals or 1,01300 pascals. The pressure exerted by air molecules is almost equivalent to putting a 1 kilogram mass on an area of 1 centimeter square. In weather forecasting, the millibars is often used as a pressure unit. 1 millibar is equal to 100 pascals. So standard atmospheric pressure is about 1000 millibars. At sea level, atmospheric pressure is about 100 kilopascals, that is 100,000 Newton per meter square, equivalent to the weight of 10 cars pressing on every square meters. But you are not crushed by this huge pressure because it is matched by the pressure in your lungs and blood system. Air pressure becomes less as you rise up through it because there is less and less weight above. Now some examples are here. Vacuum cleaner. A fan lowers the air pressure just beyond the bag. Here is a bag. Here will be a fan that actually lower the air pressure inside the vacuum cleaner. So things will rush into the bag. The atmosphere rushes in, carrying dust and dirt with it. The bag acts as a filter. So here will be a filter, stopping the dust and dirt, but not the air. Air will move out of the cleaner and dust and dirt will be collected here. Another example is here. Drinking through a straw. You expand your lungs to reduce the air pressure inside the straw. So air is inhaled. Here will be low pressure because you expand your lungs, reduce the air pressure inside the straw. As a result, atmospheric pressure pushes the liquid up the straw. Here is the atmospheric pressure. Another example is here. In the same way, atmospheric pressure forces a liquid to move into a syringe when its plunger is withdrawn, like when the plunger is withdrawn. Less pressure will be here and atmospheric pressure pushes the liquid into the syringe. Likewise, rubber suckers are used for hooks in the kitchen and bathroom. The air between the rubber sucker and the wall is first forced out by pressing the rubber sucker to the wall. Pressure will be reduced inside so that the atmospheric pressure pressing on it can hold it firmly against the wall. Another question is here, example is here, pumps are used to raise the water. So in the same case, water is pumped up into the pumps. Same formula, same technique is used in the aerosols. An aerosol spray can contain a gas which is at a higher pressure than atmospheric pressure. It is held in the can by a valve in the nozzle. When the nozzle is pressed down, a spring is squashed and the nozzle opening enters the inside of the can, effectively opening the valve. The higher the pressure of the gas in the can pushes on the liquid in the can and it rushes up the tube and through the jet where it forms a fine spray of the liquid droplets, an aerosol. When the nozzle is released, the spring is no longer squashed and pushes the nozzle upward. This removes the nozzle opening from inside the can, effectively closing the valve and stop the flow of the spray. The same technique is used in the hovercrafts as well. A hovercraft uses the pressure of the air to raise it from the ground. It does this by drawing air from above with powerful fans. There is a skirt around the edge of the hovercraft which prevents the air from escaping quickly and air pressure beneath the hovercraft increases. The upward pressure of the air trapped beneath the hovercraft lifts the hovercraft off the ground. The fans continues to spin to replace air that is lost from the edges of the skirt. The cushion of the air beneath the hovercraft reduces friction between it and the ground. The cushion of the air also maintained when hovercraft moves over water. The forward or the backward thrust on the hovercraft is provided by the propellers in the air above the hovercraft. Here is a question. The figure shows a piece of the glass being lifted by a suction cup. Here is the figure. Here is the glass. Here is the suction cup that is actually lifting the glass. Air is removed from the cup by a vacuum pump and partial vacuum is created inside the cup. There is partial vacuum is created. Atmospheric pressure outside pushes the glass onto the cup. The area of the glass covered by the cup is 0.0025. So this is the area from here to here. The pressure inside the cup is reduced to 60,000 pascals. Atmospheric pressure outside is 100,000 pascals. State the formula that relates pressure to force and to the area. So first part answer is pressure is equal to force over area. Second requirement is calculate the greatest weight of the glass that can be lifted with the cup. So greatest weight of the glass, greatest force produced by the pressure difference. So formula is pressure into force. So force will leave here, area will be multiplied with the pressure. So pressure into area is equal to the force. So pressure difference is 100,000 minus 60,000. So this is the outside pressure, this is the inside pressure. So this is the resulting pressure and area is this 0.0025. Solving it on the calculator will give us the answer. Last requirement is state two changes that would allow a suction cup to lift a heavier piece of the glass. So two changes are, number one is reduce further the pressure inside the cup by removing more air from it. And second change is increase the area of the glass covered by the suction cup. So these two changes can lift heavier piece of the glass. So this was the topic. Read it again very carefully and make your notes. Thank you so much.